Okay, good morning everybody. Let me see how many you are, and I think you are 12. Okay, so it is a reasonable number. Today we have 3 hours. We will see how they will be organized. Let me start by saying that I want to first of all make a recap of where we are. And we are, let me share the screen with, oops, sorry. It is not the screen that I want to share. Okay, this is one. I also check on the phone that everything is okay. So I can check what you see in the screen. Okay, good. Okay, so this is the web page that you see now of our course. Let me, okay, very good. Let's look at the list of the lectures. Oops, so this is one already. The list of the lecture is here. Now, we were talking about deductive methods. Remember, our purpose is, again, estimating water resources availability. Estimating water resources availability in order to make a sustainable planning of them. And we are talking about the deductive methods, which in a few words are mathematical models. And if we look at this lecture, which is dedicated to rainfall runoff modeling first, because we are now focusing on surface water. You know that our main sources of water are from surface water and from groundwater. So now we are focusing on surface water. And we talked about the rational formula, but we said that the rational formula is not really helpful in water resources management because it is mainly applied for the estimation of peak flow. In fact, we made an experiment of application of the rational formula. And if you go back to that experiment, you see that the rational formula, it's not providing a very good hydrograph. And then we focused on the first real rainfall runoff model that we considered, that we are considering, which is the linear reservoir. The linear reservoir, the theory is something that we discussed more than a week ago. And then on Thursday, we made the exercise, which was a bit hurried up. And I already suggested you to try to make an effort to gain a full understanding of the exercise, not for preparing your exam, but for two main reasons. First, because I think that it gives to you an opportunity to see how numerical modeling works. And the second thing is that if you practice the exercises, you get more and more in confidence with the PC and the programming. Keep in mind that this opportunity of getting more confidence with the PC, I already mentioned to you that it's an essential piece of your CV, the CV that you are building. But this is even more important after the pandemic, because after the pandemic, people got more and more skilled on using digital communication and using digital means. And therefore, it is extremely important that you yourself, you make an effort to improve your skills. This is what I did in my case, because I realized that there were several opportunities offered during the pandemic in order to improve my knowledge of digital working and my knowledge of computer programming. And I thought that I really saw that it became important, extremely important, because people are now being stimulated to learn more about what we can do with the computer, with the programming, and therefore it is it is, if you want to stay up to date, it is important that you make an effort in that sense. I think, as I said, the exercise was also useful because it shows the pros and cons of numerical approximation. The pros is, of course, easiness of application. And the pros, the cons are the fact that you have an approximation. And basically, you have an approximation because you work with finite differences. So you are working with discrete time intervals. And then you have several variables, input variables, state variables, output variables, which are defined to a discrete time step. And depending depending if you use them at the beginning or at the end of the time step of the computation that you make in each time step, you introduce different approximation. And this is something that I think it is extremely useful to learn. Now, there is one thing that I wanted to point out in this linear reservoir model, and one further thing I want to point out, and let me show you this formula, which you know well. Let me expand it. It's the second equation, which we used to build this model, which establishes a linear relationship between the storage in the catchment and the river flow that we want to model. And this linear relationship is obtained through a constant, which we denote with the symbol key. And this constant, the first important thing to note is that it has the dimension of a time. This is a typical question at the exam. What is the dimension? What is the unit of key and or k? It depends on how you would like to pronounce it. And so key as the k, sorry, as the unit of a time, and you can understand it if you look at the relationship on the screen. And it's clear that given that the river flow Qt is expressed typically in cubic meters per second, and the storage is a volume, so cubic meters, it's clear that K has to be a time. Now, a relevant question is, what is this K then? It is, of course, a constant which allows us to introduce this linear relationship. And it's what is called in a model a parameter. K is a parameter. What is a parameter? A parameter is an element, it's a part, it's an element, it's a piece of the constitutive equations of a model. And this piece usually takes a constant value. A constant value once we defined it. So it is constant in time, but it needs to be defined. And once it is defined, K, it's a constant in this case. It needs to be a constant, because if it wasn't a constant in time, then the model would be nonlinear. So again, a parameter is a piece in the equations that build a model that typically assumes a constant value once it is assigned. And it is introduced for the purpose of giving flexibility to the model. So K is a constant once you assigned it. And by changing the value of K at the moment of the assignment, so by changing this constant value of K, it is constant in time, but you can change it at the beginning. You can decide, like we did for optimizing our model performances during the exercise. You may remember that I changed several times the value of K. And this change of parameter values, in this case, we have only K as a parameter of this model. It is a one parameter model. We have only one parameter. And by changing this parameter, we give the model some flexibility. Flexibility to what? Flexibility to adapt to the considered catchment. So we have this catchment, which works differently with respect to another catchment. But we want to use the same model. So how can the same model work in different catchments? By changing at the moment of the assignment the value of the parameter k. So the parameter is an important piece of a model because it gives flexibility, and we need this flexibility because catchments are all different, and we need to adapt our modeling to their shape, to their geology, to their storage capacity, to their functioning, to their dynamics. And therefore, we adapt the model to these different catchments by changing the k value. And you may say, is it enough is it enough changing the k value to apply the model to a so huge diversity of catchments? I would say yes and no. Sometimes it is enough. Sometimes we find catchments for which, even if I try several different k values, it is not possible with the linear reservoir to reproduce them well. So parameter is equivalent to flexibility. And if I can't find any value of this parameter, so if I can't find any flexibility that allows me to well simulate a catchment, what now can I do? I can change the model. And a different model may have, for instance, more than one parameter, which means more flexibility. The linear reservoir has only one parameter, little flexibility. If I change the model, a different model may contain 2, 3, 4, 5, whatever number of parameters. And then flexibility is increased. So the next step of our learning is precisely to give you an example of a further model which is more flexible with respect to the linear reservoir. And what is this next model? Let me now go back to our web page. If you scroll down after the linear reservoir, we talked about the nonlinear reservoir. And this is another example. It's a possible example. We could try to write the code for a nonlinear reservoir in the way we like it to see if things improve. But we are not making any application of nonlinear reservoir. What I would like to do instead is to illustrate another model which is called Imod. So this is our next step. On the other hand, I would like to wait a little bit before doing that. And this is different with respect to what I did in the past. In the past, after the linear reservoir, I lectured the Imod model. But given that Imod it has some more complexity, and it is something that requires a lot of attention, I would prefer, before then Imod, to focus on the topic of how can I calibrate the parameters of a model? This is another question which I would like to focus on. So for instance, let me refer to the linear reservoir. How can we determine the value to give to k? This is the next question. You have already a first answer because we did it in the exercise, but I would like to discuss this issue of guessing the parameter values in more detail. And usually this is the next topic. So after discussing the Imod model, usually with students I discuss this next topic of guessing the parameter values. This year I would like to anticipate it, because I think that if you already know how to guess the value of the parameters, then you may also better understand how this subsequent model, Imod, works. Okay, now, let then me go to this topic of guessing the value of parameters. And in order to do that, I go back to the list of lectures and I take the next one. And this is the lecture I would like to focus on with you today. I don't have a PowerPoint for this lecture, so I'm using the web pages with some particular focuses on other figures that I will use. First, let me make a further premise by recalling what we did, because we applied the linear reservoir, and actually, as I mentioned before, we already had an experience of guessing the best parameter value. So let me refer to that, and let me note that in the exercise, what we did was a trial and error procedure. So we tried several different values, and then we continued trying until we were satisfied, until we were happy. And what was the condition to say I am happy with this parameter? The condition was a comparison between the model simulation and observations. And let me say that this is at the basis of what we discussed today. In order to guess the optimal values for the parameters of a model, the main road is, the highway is the comparison between model simulation and observations. This is something that an engineer should always do in order to check if a model is reliable. And sometimes you may not be able to do it because you don't have any observed data. And then if you cannot do it, there are alternatives. But the alternatives are much less reliable, much less reassuring in terms of making you relaxed with respect to technical applications where you put your signature below it. So keep in mind, comparison between observations and simulations, which is also called assessment of model performances. It's also called goodness of fit testing. Okay, again, assessment of model performances, goodness of fit testing. And I am really stressing this issue because you really need to take it in mind, because today it's not so clear that this is the basis. It's not so clear because there is an increased use of mathematical modeling for engineering. There is an increased use. I can make you many examples. So for instance, estimation of flooded areas, or decision theory for water resources management. There is an increased use of mathematical models, which is fine because they give an enormous opportunity to the engineer. It is fine. I mean, you shouldn't refrain by using mathematical model. Absolutely, you shouldn't refrain from it. On the other hand, you have to be careful because using mathematical models, basically you are still representing the reality. It's not a virtual reality, it is a virtual reality that represents a true reality. So it means that you have to be extremely careful in checking that the models that you use provide a good representation of reality. And as I said, if you look at the literature, it is becoming less obvious. So this is the reason why I really want to tell you, be careful in your profession, in your career. This is the master way. And then I will give you some examples later on where the literature doesn't tell you this. And you have to be very careful because, as I said, as engineers, we have a responsibility. We have a professional responsibility, which a scientist doesn't have, essentially. So if I propose a wrong theory, okay, my reputation is undermined, but I don't have a professional responsibility. As an engineer, when I sign a design project, I have a professional responsibility. So keep in mind what is the master way. It's comparison of observation versus simulation in a way that must be rigorously laid out. And this is what we discussed today. So given that we want to make this comparison, how can lay it out in a rigorous way? Now, let me make a premise on terminology. We are now discussing guessing the best parameter values for a model. This is not a technical terminology. In the technical terminology, I would say model fitting. Model fitting, which means find the best way of parameters, the best value for parameters. Or I may say model calibration. I may say model optimization. I may say model parameterization. I repeat, because these are synonyms. Model fitting, model calibration, model optimization, model parameterization. These are all synonyms for guessing the value of parameters. You shouldn't say I'm guessing the value of parameters. It looks like guessing is not professional. In professional terminology, usually the most used one in engineering is model calibration. But it is also fine if you say model fitting, model optimization, model parameterization. Validation, which you see on the screen, is a different thing. It's not a synonym of calibration. I will explain to you what's the difference between calibration and validation. Now, very good. So, what are the methods that we have at disposal for performing? Just 1 second. For some reason, I need to, in the phone, to put back the credential of my Teams. 1 second. Okay. Good. Let me, okay, very good. Perfect. So, what are the methods that we are available for making this process, for making model calibration? We have the methods fall into 2 categories. First of all, you see that we discuss now we give an example here, which is basically what I said before. Mainly, it's a comparison between observation and simulation. This is an hydrograph, and this is what we did with the exercise, but we did it with respect to a very long hydrograph. Here, it's just, you know, it's first of all, I see that there is the visualization, which is misleading because in the horizontal axis, I never noticed it. You see that there is, no, it's fine. 0 is midnight. It is fine, sorry. And it is referred to this, it's referred to 3-4 days. So it's a very short hydrograph. And this is our basis. And in fact, you see that the title of the section is Calibration through Optimization of Model Performances, which means comparison between observed and simulated data. It is not the only one. I mentioned to you that if you don't have any data, there are alternatives, okay? And we will also discuss the alternatives. But you have to remember that this is not the only one, but it's the master way. Now, these basically techniques, optimization of model performances, fall into two categories. The first category, let me see where it is written here, and let me, okay, here. The first category is trial and error procedures. Let me increase the font, okay? And it was the most used approach in the past. It is what we used in our exercise. And so what is a trial and error procedure? You try, you guess a value for the parameter, and then you try to run the model, and you see the model performances. And then if you're happy, you stop your calibration. If you are not happy, you guess another value. And again, this was the most used approach in the past. And why it was the most used approach in the past? Because in the past we didn't have many computational facilities, and therefore it was this is the simpler way. It is the simpler way. You don't have to make complex computation. You just run the model several times. Okay. Because you will see that the alternative to trial and error is a bit more complicated, at least not for us, because you will see that for us, with a good PC at hand, probably it's very easy. It will be very easy also for you. But in general, in terms of calculations, if you refer to a time where people had to make hand computation, it is more complicated. The alternative. While running a model with a guess value for parameters, it's not very complicated. Okay, and now the problem is, how do you judge if you are happy? Because with trial and error, you have to, every time you make a trial, you have to make an assessment. Are you happy? How can you assess if you are happy? So it can be a visual comparison. Like, let me see again this figure here. So visually, I can say that the simulation is fine. Of course, you need some experience in order to make a visual comparison. And some experience in a way that allows you to say that you are happy. And also, you need some experience in changing the value, changing the trial value of the parameters according to what you see. Like, if you look at this figure that you see on the screen, I may ask you the question, if you had to guess an additional value for the parameter to improve this simulation, how would you guess it? Because the guess, you know, if it is a guess just by chance, like you throw a dice, okay, you can do this, but actually it may take a long time. If you remember what I did in the exercise, I started by increasing the K value, because what I said was, if you remember, I said, look, the hydrograph is, the simulated hydrograph gives two high values with respect to the observed one. You may remember that the observed one was around 200, while in the first trials we got a simulated one with max of 1000. So I said, two high flows. I have to reduce the high flows. And I said, I know that in order to reduce the high flow, I have to increase K, which is intuitive if you think at the model, on how the model is built. If you increase K, you decrease your outflow. If you look in the linear reservoir, how the model is defined, you may remember that the outflow is given by storage divided by K. So it's clear that if you increase K, you decrease the outflow. And this is your experience. This is experience means that you know. It doesn't mean that you are old. It means that you know. So if you know how the model works, you can guess the value of the parameters. And you can say, I am happy with this simulation. Because, for instance, with the linear reservoir, I wouldn't try to reach a so good simulation as the one that you see on the screen. To me, it's clear that the simulation is not obtained with the linear reservoir because it's too nice. The linear reservoir, it's a bit rude as a model, it's rough. So this is some experience that you gain by trying different models in different catchments. I will give you some rules of thumb that allow you to decide. But the main story is that if you want to use trial and error, you need some criteria for saying that you are happy. And visual comparison may be one. Okay, so let's say that this is what is applied in many times. And I also would like to say that whatever model you use, a visual comparison is always helpful because it gives to you a touch of what's going on. Never evaluate a model, never say that you are happy with the model without looking at the output in a graph. Because a graph, it's something that gives to you a synthesis, gives to you a picture, an overall overview. If you just look at numbers, you don't get a good feeling. The graph is something very good. So visual comparison is something very useful. But there is to say that you may want to get a more quantitative criteria. Okay, quantitative means that visual it's qualitative, it's not quantitative. You may want a number that quantifies the goodness of the fit. Because a number may help you in assessing whether an alternative is better than another one. When you have a number, you compare two numbers and you see what is the best. Okay, so if you were able to score your result in a grade between 1 and 10, of course, if you have a parameter that gives 10, it's better than a parameter that gives 9. So we need, the idea was to look for some quantitative criteria. And quantitative criteria, I'm scrolling down the page, and quantitative criteria have a disadvantage that they require some computation. The visual comparison doesn't require any computation. Very good. But let's look at this quantitative criteria and look at this row here. Such numerical criteria were identified by devising objective functions or loss functions, which are function mapping values of one or more variables into a real number, intuitively representing model performances. This is what I want to discuss now with you. So, a numerical criteria that it's obtained through an objective function. What is an objective function? Here there is a link, let's see. In mathematical optimization, which is what we are talking about, and decision theory, a loss function or cost function is a function that maps an event or values of one or more variables into a real number, intuitively representing some cost. So an objective function is either a loss function or it's negative. It's a matter of assuming, of making assumption. Why here it is said that an objective function is either a loss function or it's negative? Because, of course, the negative of a loss function is a benefit function. So if you want to seek the max benefit, you have to put the cost in negative terms. That's the meaning. Okay, let's close this page because we don't want much details. Now, what could be an objective function for our application of the linear reservoir? Okay, let's see. Objective function, here we have a section. And let me start with an example that refers to the most used objective function, which for sure you already know. It is the sum of squared error or sum of squares. Now let's open this equation and let's maximize it, because this is my objective function called sum of squares, or it is also called sum of squared errors. And be patient if you already know it. I want to discuss it because once that you understand the rationale behind this very simple objective function, then we are halfway to our target, because other objective functions are basically an extension of this one. So let's suppose that you use the model to simulate capital N observations. Okay, so you have capital N observations, like, I don't know, 10 observations, 100, 1,000, 1 million, no problem. Then you get, for each of these observations, a corresponding value simulated by the model. Here, the observations are called x as a function of time, t. So if you look at the square parenthesis, it's the left addendum, xt. The model simulations are indicated with the symbol x at t. So the at indicates the value simulated by the model. Now we can make a difference between observation and simulation. If the simulation is perfect, this difference is 0. This is, of course, fine. And if this difference is in absolute value is large, then there is a large error. Okay. Now we compute the difference. It is intuitive that the difference is an indicator of model performances, of course, because 0 is perfect. The larger the difference, the larger the error. Now, I square this difference. Why do I take the square? Okay, let me give you a very simple reason for that. Because I want to avoid compensation between negative and positive errors. So by squaring, I eliminate the sign. This is a first reason. I'll give you other reasons later. Now, I take for each observation this difference squared, and then I sum all the squared differences. And therefore, I obtain a number f, which is capital F, left-hand side, which is a function of what? Of the value of the model parameter theta. And keep in mind, theta may be one parameter. In the linear reservoir is only one, or, as I said before, can be a vector of parameters. Good. So f theta is the objective function. For each theta value, for each parameter value, I get a different objective function. And the larger the f, the larger the error. If f is 0, the model is perfect. This is very intuitive. And this is the sum of squares. And now a criteria for optimization, calibration, is called the least squares, which means you can find the value of theta, which gives you the minimum for f, the least squares. This is a criteria for optimization. Keep in mind that model calibration and validation is a usual question at the exam, just to make you aware. And it is also a usual question because it's quite, it's not a very complicated topic, as you see. And the complication is at this level. I'm not going to say anything more complicated than this. Which means, in a way, that if you have any question, you should ask me, okay? Because I am really assuming that everything is clear here. And if it's not, I mean, the lecture that I gave on Thursday, I understand that there must be something not clear. And this is why I told you, please, you have the video, do it again and try to make sure that you really understood. I realized that it was a complicated lecture. Today, I am assuming that everything should be clear. If it's not, you don't have any problem in resolving your doubts. Just write a question. Let me know. I can repeat. Okay? Very good. Now, you may say, but why do you need to square? Because if you want to avoid the compensation between negative and positive errors, if you want to remove the sign, you could take the absolute value. True. In fact, I believe, let me see, that this solution is the next objective function. Let me see just 1 second. It's not the next, but I am quite sure. Here it is. Here it is. You see, here I take the absolute value of the difference. F theta is equal to the sum between 1 and n of the absolute difference between model simulation and observation. So you may say, what's the difference? They are clearly two different objective functions. And let me say one thing, just to explain in a very simple way their difference. If you square an error and you take the sum of squares instead of sum of absolute values, what you do is to put emphasis on the larger errors. Because, you know, if the error is small, it's 1, for instance, the square of 1 is 1. If the error is 10, the square of 10 is 100, which means that an error of 10 is giving a larger contribution to your objective function than an error of 1. Keep this in mind because it's extremely important. In the formation of your objective function value, the larger error, if you square them, take the whole of it. And the smaller errors are basically ignored. Okay, this may be fine. But when do you have the larger errors in a rainfall runoff model? You get the larger error when you simulate the high flows. Because if you simulate a value of 1000, whatever the unit is, it's clear that if your simulated value is 900, the error is only 10%, which is fine. It's a good approximation in hydrology. But the squared error is 100 squared, which means 10,000. So it's very large. If you simulate a value for a river that is 1, and you make an error of 0.5, it's a very large error because it's 50% of it. So it's very large. But if you square it, it's 0.5 times 0.5 is 0.25. It's nothing compared to 10,000. So it means that the sum of squares gives more weight to the simulation of the high flows. So this is another reason why the error is squared. Because if you are interested in the simulation of the flood flows, we should square the error, and we should ignore the errors that are done in the simulation of the low flows. Good. But in our subject, we are more interested in the good simulation of the low flows. And therefore, the objective function that you see now on the screen sum of absolute errors may be more appropriate. So it's up to you, but you have to be very careful, very knowledgeable, very informed. When you select an objective function, you must know the reason why you selected it. Furthermore, there is one more thing that I would like to say. Probably it's the less important, about the least square objective function. And let me go back to it. Okay. Sorry. Here it is. There is one more thing that I would like to say about this objective function. And in statistics, one can prove that under certain non-limiting assumptions, which we don't need to know, in statistics, it can be proved that with theoretical proof that this function, sum of squares, works better than the sum of the absolute values. What does it mean that it works better? It means that its uncertainty in giving you an assessment of model performances is more limited. Overall, I mean overall. Overall, what does it mean overall? Overall means that it is referred to this statement, uncertainty more limited, to the whole range of the river flows. So given that I have to make a unique comparison, a unique assessment with a unique number of the overall model performances in simulating low flows, high flows, etc. So there is a theoretical proof that says that overall this is the objective function that works better. Now, overall doesn't mean that it is good in the low flows, because this is precisely what we said before. For the low flows, it's not good. So, I mean, I can ignore this overall evaluation of objective function if I am interested in a specific range of river flows. So again, if I want to simulate low flows well and I don't care about high flows, I can forget about the objective function that you see on the screen now, squared. And I should use the sum of the absolute values, because I am interested not in the overall performances, but in the low flow performances. But again, it is interesting that I say, and that you know, that overall there are proofs in statistics that say that this objective function is better than the sum of the absolute values. And here you can see a long discourse on this. And it's in more technical terms. You see here, I introduced technical terms in statistics: consistency. Consistency is a way to measure uncertainty. So I said uncertainty is limited, which means that consistency is higher. I don't want to discuss with you what is consistency. Unbiasedness, another measure of uncertainty. When I say uncertainty is limited, I also mean that unbiasedness is fine. Okay, for least squares, for sum of squares. Good. If you take the sum of the absolute values, you may have some bias. You don't have unbiasedness, and you don't have consistency. Again, I'm not interested in discussing these terms with you. I'm just saying that here there are the links. If you are interested, has, I would say you should, in some more detail, you can look at it by yourself. I don't want to take your attention on something that we can summarize with simpler words. Okay, good. Now, let me introduce now a third objective function. And here it's the introduction. And let's see it. And first, let me say that this is an objective function that has the same properties as sum of squares. The same properties. So the properties, I mean the fact that it emphasizes the high flows and it's well behaved in statistical terms. Let me see the objective function. Let me put it on the screen and expand it. Okay, first, how it's called. This is called, this objective function is called Nash Satcliffe efficiency. And please make an effort to remember it because it's important. Again, Nash Satcliffe efficiency. Now, you see that you recognize in the right-hand side, the second addendum, you recognize the numerator, the sum of squares. So you understand why it has similar behaviors as the sum of squares, because the numerator at the right-hand side, it's the same. But it is rescaled by what? Look at the denominator. The denominator is the summation of the difference between model simulation and the average X bar of all model simulations. So this denominator doesn't depend on theta. The only thing that depends on theta is X hat. Okay? And now, the denominator, let's look at the denominator. It doesn't depend on theta. It can compute it only based on the observations. It is the sum of squares, the sum of squared errors with respect to the mean or average, whatever you call it. So you have a series of observations. You compute the mean of the observations, and then you compute the sum of the squared differences between observation and the mean. It is like you used a very simple model for making your simulation, which is the mean. Which could be, I mean, you could also say, why should I apply a so complex range for an off model? Let me take the average value of the observations as model output. It is a constant output, so it would be a very naive prediction, probably not useful in technical terms, so this is why we don't use it. But still, it is a good reference because it is the prediction that people tend to do if they don't have any information at all. Like if you have observations, numbers, and you have to predict the next one, and you don't know anything. You don't know what the numbers refer to. What should you do? What is your best prediction? It's the average. You compute the average and you say, okay, for me, the next one will be like this number, which is the average. So it is something very naive, but also something that it's, I mean, not unreasonable if you don't have any information. Of course, with a model, we try some more because we have more information. We have rainfall as input. We have several informations that we can use. We know that the numbers refer to river flow, so we can build a linear reservoir. Okay, but then if I apply this model, let's divide its sum of squares by the very naive, by the sum of squares of the very naive prediction. So if you look at the right-hand side here, and at the second addendum, at the numerator you have the sum of squares of your model. At the denominator you have the sum of squares of the very naive prediction. And what are you expecting here? You are expecting that this ratio is lower than 1. Because if this ratio is 1, it means that, the sum of squares of your model are equivalent to the sum of square of the very naive prediction, so the model is useless. But you are expecting that this ratio is lower than 1. And you may expect that this ratio is 0 if the model is perfect. You may also expect, if your model is plain wrong, that this ratio is higher than 1, because the model may be worse with respect to the very naive prediction. So here you have something varying from 0 to infinity. If your model is infinitely wrong, this ratio diverges to infinity. Now, what is the purpose of computing this ratio? Precisely to compare the performances of your model with the performances of the very naive model. And then, if you look at the whole right-hand side, you see that here you have a difference between 1 and this ratio. Okay? Why 1? Because I said that if this ratio is 1, it means that the model is useless. So if you look at the whole right-hand side, 1 minus 1 would be 0. So I think that this is a good indication of model usefulness. If f theta here is 0, what does this mean? It means that the model is just useless, because the performances are the same of the very naive one. Conversely, if f theta is 1, because the ratio at the right-hand side is 0, then the model is perfect. Good. So we have an overall range of variation of the right-hand side between minus infinity, because I said that the ratio may go to infinity if the model is infinitely wrong. So the range is minus infinity 1, where the interval of interest is between 0 and 1. If you get an f that is lower than 0, then the model is absolutely to be rejected. If you have an f that is between 0 and 1, the model may be evaluated because it is better than the very naive prediction. So what is the usefulness of this objective function? What is the nice behavior? The nice behavior is that you have a term of comparison between different models and watershed, because the only sum of squares is just a number that is typically very large, that doesn't tell you anything. What does it mean if you have a sum of squares of 10 millions? It may be a very good one or a very bad one. You don't know. Instead, if you use the Nash Satcliffe, a sum of square of 10 millions may turn out in a f theta of minus 10, which means very wrong. Or it may turn to a sum of squares of 10 millions, it may turn to a f theta, which is 0.6, which would be very good. So it is an objective function that is equivalent to sum of squares, but it allows you to get term of comparison. And in fact, for the Nash-Satcliffe efficiency, we have some rules of thumb. We say that usually, in hydrology, for a rain-for-runoff model, we usually say that a Nash efficiency lower than 0.5, it's very poor. It's a very poor model. We start talking about a useful model when we are around 0.5. I'm talking about rain-for-runoff modeling. And rain-for-runoff modeling is usually performed with hourly or daily data. When we get a Nash efficiency greater than 0.7, we start talking about a good model. Greater than 0.9 is a very, very, very good model. Usually, we don't obtain such good performances. So this is another important objective function which I suggest you to remember my memory. And I think these are the only 3 examples. No, there is one more. Yeah, I forgot. Let me give you another example, but before than that, let me go back to the sum of absolute errors. We call this objective function sum of absolute errors. Now, there is, what is the advantage of this objective function? The advantage is that it puts emphasis on, just 1 second, I need to put the charge on my headset, 1 second. No, actually not. I got a beep and I don't understand what's about. Okay, now I see. There is a student in the lobby. Very good. And so let me say again, sum of squares, sum of absolute errors, sorry. The sum of absolute errors, we said that it's good when we want to put emphasis on the low flows. Perfect. But what if we want to put even more emphasis on the low flows? Even more. Okay, so another alternative, it's for low flows, it's this one. And this is called sum of absolute relative errors. Basically, I minimize the sum of absolute squares divided by each observation, which, if you think of it, it's the larger the xt at the denominator and the lower the emphasis. So the lower the contribution of that observation to the formation of the objective function, which means that if you divide, if you take the relative error, then you have an increased emphasis on the low flows. What is the problem? The problem is that it's increased a lot. And in particular, if you have xt at denominator tending to 0, then you get this contribution tending to infinity. The corresponding error tends to infinity, which is something that we want to avoid because, you know, when you have few terms dominating, it's always a situation that you don't want. When you have few observations dominating in the assessment of the performances of your model, you want to avoid it. And so this is something that you shouldn't use if you have the feeling that xt may approach 0. If xt doesn't approach 0, this may be fine. And but you have to be careful. And this is something that when I talk with colleagues, I realize that not all of my colleagues are aware of the problem of river flow approaching 0. And I see that this is something that I well know, because in Italy, most of the rivers I'm dealing with are intermittent. So there are zeros in the observations. And but I had a conversation just a few weeks ago with a colleague working in the United States on large rivers mainly, because he's working at the United States Geological Survey. So they are not concerned by ephemeral rivers, small rivers. They are more concerned by the large rivers because they work in a completely different context. And I realized that he was not caring about the chance that the river flow may be 0, because it's not a frequent experience for them. For an Italian hydrologist, I replied by saying, look, I would say that 90% of my applications refer to rivers that may have, if not 0, river flows that are very close to zero. So the use of this objective function in the Italian context is very unlikely. And but in any case, it is useful to know it because it's a way to put emphasis on the low flows. And another solution may be, of course, to take the square root instead of the absolute value, to take the square root of the absolute value of the difference. And the square root is the opposite of course, of squaring, and so you get the more emphasis on the low flows. Okay, so these objective functions, let me put them in the overall context from which we started, may be helpful for you if you are in a trial and error context to get a quantitative assessment of model performances, as we said. Okay, good. Now, let's go back to our page and let's now see an alternative to trial and error. What is the alternative? And just 1 second that I find, okay. And let me emphasize this sentence. Sorry. Let me emphasize this one, which says that with the advent in the late 80s of the past century and 90s of personal computer, which quickly provided unprecedented computational means, the researchers devised automatic procedures for parameter calibration. So the availability of the personal computers and the computational means suggested to devise something more comprehensive with respect to the trial and error procedure, and to devise something that was automatic. Because, of course, the trial and error, it is good because it gives to you a perception of what's going on. So you get a parameter value and you get a perception of what's going on. This is very good. On the other hand, the trial and error has the disadvantage that it takes a lot of time. It takes a lot of time, and it doesn't allow you to explore all the possible values of a model parameter. You may remember, for instance, in our trial and error exercise that I jumped with very, very large steps towards larger key values. But every time I made a trial, I made a huge jump forward. And it may happen that by doing only few trials, you miss good values. You miss good trials. If you make the trials automatically, of course, it's more comprehensive. You can leave the computer running overnight, and then in the morning you get the result. And this cannot be done with the visual approach, because visual approach requires your intervention. But if you use an objective function and you want to find the value of theta that minimizes the sum of square, it can be done automatically. The computer evaluates for each trial the result of the sum of squares and makes another attempt. And if the second attempt gives a sum of square that it's lower, then the second attempt is retained. It's a simple programming that only requires putting some conditions. Actually, if you make automatic calibration, you may also introduce a guided search. So you can use your knowledge to dictate instruction to the computers to guide the search, which means faster convergence. Like, for instance, you may tell the computer, look at the peak flows. If they are much higher of the observed flows, then don't decrease the K value. Only look for increasing values. And this is a way to make the procedure automatic and guided, which is, I mean, something that can be done. And this is automatic calibration. And these automatic calibration procedures, we don't say much because let me just say that they use the objective functions. They cannot make any visual comparison. So some of my colleagues, for instance, say, okay, let's make it automatic, but I want to see a visual comparison every, I don't know, 100 trials in order to make sure that everything is fine. And so this is something that can be done. For instance, you may produce a PDF with the graphs, with the hydrographs observed versus simulated every 100 trials. That's fine. This is something that we usually do, this automatic calibration, by applying a pre-prepared software. And this is why I don't want to discuss with you about these procedures, because you can rely on them. Of course, you may say, yes, but at the beginning of the course, you told us that we shouldn't rely blindly on software. In fact, this is not what I'm saying. You may apply blindly an automatic calibration procedure. In R, you have many of them. And then at the end, when they give to you the result, you have to check. You have to check if the performances are indeed fine. I mean, so this is not blind application, but it is application with expert knowledge of something that is prepared by others, because it's not under our remits. I mean, writing an optimization algorithm, it's not under our remit. And the use of this automatic calibration and guided search becomes particularly important when the model is complicated and you may have like 10 parameters to optimize. If you have 10 parameters, how can you make your trial and error procedure? How can you judge every single combination? It's impossible if you have 10 parameters. So basically, it was a combined process. The awareness, the availability of computing resources stimulated the development of more complicated models with more parameters because they are more flexible. They are more flexible. On the other hand, they required a more sophisticated calibration procedure, which was aided by devising optimization algorithms that are able to make a guided search. As I said, these algorithms, you have plenty of them available with R, and we will make another exercise where we will apply the Imod model, which has 5 parameters, so it's more complicated. And we will estimate these parameters with automatic calibration algorithm. So at this stage, our optimization calibration problem is resolved. We have 2 main options. First, we have to remember that the master way is comparison of model with observations. Okay, if we stay in this category, then we have 2 main options, trial and error, automatic calibration. If we go with trial and error, we know what to do. We don't need any objective. We may say that we don't need any objective function because we rely on visual comparison. If we instead decide to go with automatic calibration, it's better if I use an objective function. I need an objective function, which can be used also in the trial and error, but it's less needed. In this case, with automatic calibration, I really need it. And then I can use one of the several algorithms that are available under the different platforms. Excel has one, MATLAB has another one, R has plenty of them. Good. So I think that calibration is, in this case, is resolved, but we still need to talk about what to do if I don't have any observation. So I cannot compute any objective function. Let me see where it is discussed in my web page. This I don't remember if it's yeah, calibration through expert knowledge. This is what I wanted to discuss. Before I get into this discussion, which is not very quantitative, it's mainly discourse. I want to ask you if you have any question on the objective functions, etc. in what we discussed so far. Okay, no questions. So what to do before I make the break? So I still have some minutes. Let me go to 10:50, given that I started a bit later. And so what to do if we don't have any observation? And this is a problem that occurs quite frequently. First, we have to be aware of the uncertainty. We have to be aware that we are not relying on an essential requirement for model calibration, which is, as I said, the comparison between observations and model. We cannot rely on it, and therefore we have to be fully aware that the uncertainty is much higher. If we turn into technical design, it means that we have to be very careful in order to try to use all the available information to minimize it. Okay, awareness first thing. And then there are options. And the option may be, for instance, to refer to a neighboring catchment, which is very similar. Again, hydrologic similarity. So if the neighboring catchment is very similar, then we can say that the parameters for the neighboring catchment can be transferred to the catchment of interest because they have similar climate, similar size, similar reaction to rainfall, etc. And then we may simply transfer the parameters. And for instance, for the linear reservoir, one could say, okay, the two catchments are so similar that I believe that the K value is the same, which is something that may be reasonable. And another solution may be to base the calibration on your own experience. And here there is written what I meant to say now. When calibrating the linear reservoir rainfall runoff model, one may decide to set the bottom discharge time constant by equating it to the time of concentration of the catchment. Because this is what we already discussed. The time of concentration is related to the K value. But actually, this is what I did when we performed our exercise last Thursday. The first guess that I made for K was the time of concentration. And then we saw that it was not enough. I had to make a long trial and error procedure. So I mean, one may indeed use expert knowledge, one may indeed use what has been observed for other catchment. The literature proposed also several other approaches, which are all based on the same two concepts that I just introduced: expert knowledge, comparison with other catchment. And for instance, the literature tried to make multiple comparison with several other catchment instead of only one, and with more or less sophisticated approaches, but still expert calibration is subjected to a relevant uncertainty. Okay, so I'm not discussing anything more than that, and I just want to say that it is an alternative, but once again, I just want to say that the master way is comparison with observations. Very good. Now, let me introduce in a few minutes the next topic, which is model validation. As I said, it's not a synonym of model calibration. I really would like to draw this attention to validation because it is essential for an engineer. And I don't know for what reason, usually students don't pay attention to it. They think it is just a corollary of the overall discourse on model calibration. And therefore, when I ask at the exam this question, what is the difference between calibration and validation? Very often it is a tough question for students. It looks like they don't care about it. And so this is why I want to draw your attention, because it is a usual question at the exam first. Second, it is extremely important for an engineer, what we call model validation. So please don't underestimate its importance, okay? Now, what is then validation? It's a kind of check of the goodness of your calibration. I mean, you calibrate a model, you wanna, at the end of the story, I told you that you should make a check of the goodness of the fit. How to make this check? Is validation is one of these opportunities. You can make a visual comparison. You can make whatever solution, you can apply whatever solution you think appropriate. One of these solutions is validation, which is the most codified one. It's the most widely used. It is often associated to visual comparison and to other quicker procedures. Okay, before I would like to make the break. Before I get into model validation, I wonder whether you have any question before we make the break. Very good. So let's take the break. See you in 15 minutes from now. Thank you very much.
Okay, Professor.
Do you have a question? I didn't understand. Do you have a question?
No, I was saying okay.
Okay, thank you very much. Okay, see you later then. Okay, so let me just share the screen just for a little while. Do you have any question again? Let me check. Nothing. Okay, so let's go back to model validation. Here it is. Okay, so first, why is model calibration? Why model calibration needs to be checked? Needs to be verified, validated, because the term validation stands for validating the calibration. We say, very often we say validate the model, but actually what is implicitly stated is that we validate the model parameters. Okay, so why do we need to validate the calibration, the parameter values that we have estimated? The reason is that, first of all, you know, automatic procedures may be always subjected to some uncertainty, and they may be well wrong. And but this is not really the primary reason. I mean, even if you performed a visual comparison, a visual assessment of calibration, and then you already verified that the calibration is meaningful, even in this case, validation is something more, something that you should anyway carry out. So validation is something more with respect to checking that the calibration went well. Validation aims to confirm that indeed the model is providing to you a good technical support, which is beyond, it's more than assessing that calibration went well. Because a model can be well calibrated, but still it may give to you a poor technical support. Why is that? Because the model, if it works well in calibration, may still be poor in reproducing a situation that it's new to it. So let me make another example. You make a trial and error procedure or an automatic calibration procedure, and you optimize the functioning of the model with respect to a specific situation. Like, for instance, let me give you a very trivial example. Let's suppose that you have data only for the spring season. You perform a model calibration, which may be perfect, and the model gives to you very, very good performances. But then you are not allowed to conclude that in the fall season, which is something that is out of the calibration context, the model works well. So it's calibration. It's always a training with respect to a specific situation. If this specific situation on a conceptual level, if this specific situation is extended enough, so it becomes more general situation, then you may be more confident on the model performances with respect to something new to it, because the training was done with respect to a very comprehensive set of situations. But if the calibration was referring to a limited limited context, then when you put the model in front of a new situation, out of context, we say in technical terms, out of calibration sample, then the model may be very poor. So validation aims to check the model and the model parameters with respect to a new situation, a situation that the model was not trained for, a situation which is out of the calibration sample. This is the purpose of validation. So basically, you want to make sure, you want to test the model performances in a situation that it's similar to your design. When you make a design, you couldn't really train the model for that design. It's a new situation. And therefore, you want to make a preliminary check that the model, if put against a new situation, new with respect to what? With respect to the calibration sample. So you want to check that the model, when put in front of a new situation, is reliable. So how to do this? You know, you need data, because validation is again a comparison with observed data. But this observed data should not have been used in calibration. How to do this? There is the most used procedure. It's called split sample validation. And let me check. I think it is written somewhere here. And let me, okay, here it is. I saw it, split sample. Let me see. Let me check in my web page, split sample, okay. A simple and intuitive way of performing validation for a hydrological model is to use the so-called split sample procedure, okay? So according to this procedure, read what follows here. The observed data are divided into two groups. One group is used for calibration, and the other group is used to test the model by emulating a real-world application, namely by performing an out-of-sample application. It is very simple. Like you have 10 years of data, you use 5 years for calibration, and then by using the calibrated parameters, you simulate the other 5 years. And then you are testing the model with respect to an out of calibration sample situation. And this is the way validation is more frequently performed. Okay? And of course, there is a disadvantage here. The disadvantage is, and look, please try to be concentrated on this discussion, because it's extremely important for both exam technical application. So what is the advantage of validation? It is clear that you want to test the model with respect to an out of sample situation. Good. What is the disadvantage? The disadvantage is that you are not using part of the data for calibration, because if you have 10 years of data and use only 5 years for validation, for calibration, then you are missing the advantage of using the other 5 years for calibrating the model. So the split sample procedure is something that, you know, it's a bit problematic in terms of optimal use of information. So what it is usually suggested in the case of the example that I made before, 10 years of data, it's you know, maybe that the split sample is not to be done 50-50. So not 5 years for calibration and 5 years for validation. Probably the best way forward is 9 years for calibration, 1 year for validation. And in this case, of course, validation is short, but still it is a good example. And also, what you may do in this case is to rotate the year that is left out. So if you have 10 years of data, and you decide that 9 years are used for calibration, and 1 year for validation, then you can make validation 10 times by rotating the year that is left out. Okay, so you get 10 exercises of validation, and you have 10 indication of model performances out of sample. I saw a question, so I give it to you the word in a moment. And you have 10 set of parameter values, because you are making also calibration 10 times. And just try to follow me in this reasoning, okay? So, I'm sorry that I don't have the graphic blackboard today because I am in my office, so I cannot make a sketch for you, but just keep in mind this example: 10 years of data, and then you left out the first year, and you perform calibration with the years from 2 to 10. You get one parameter set, one indication of model performances. Then you leave out the second year, and you make calibration with years 1 and from 3 to 10, and you validate on the second year, and you have a second set of parameters and a second indication of model performances. At the end of the story, you can take the average of model parameters and the average of model performances. This is called Jackknife validation. I give the word, there was a question, and please feel free to write on the chat, or oh, I don't see any more raised hands, just 1 second. So I guess that you just wanted to tell me to admit the student in the lobby, or no, no, there is a raised hand, yes, please.
Hello.
Yeah?
It's not really a question.
It's not a question, so what is
No, if you can take back the process of validation of for the hydrological model, the spill sample procedure.
Okay, you wanna that I explain back. Okay, let me just give you, let me make an attempt to open a graphic blackboard. Just give me 1 second. And I have to draw on the mouse, so you have to be patient with me. Okay, and let's go. Okay. Now let me take. Let me draw a straight line, which is my observation period. So here it's my observation period. Just 1 second. Observation period. Okay, good. This is my observation period, and let me just move this in years. Oops, sorry. Here it is, observation period, and let me just check here years. Okay, and let's put here, this is year 0, so let me just write here 0. Okay, and let's indicate year 0 here. 1 second. Okay. Yeah, didn't work. This is year 0. Okay, and let me now put the other years here. Just 1 second. Okay. This is year 1. Okay, good. And now let me just duplicate this. Just 1 second. Okay. And let me put the other years. Oops. So this is something like here 2, and this is something like here 3, something like here 4. Okay, and something like here 5. And let me limit the example to 5 years. Just 1 second, there is still waiting in the lobby. Okay. Okay, this is the example for 5 years, and let me just now put here, this is year 1, this is year 2, this is year 3, okay, oops, 3, this is year 4, and this is year 5. Let's suppose that we have only 5 years, okay, because in this way it's easier. Now, instead of calibrating the model on the whole period, let me use a split sample procedure. So the split sample procedure is such that, let me take the red color. Okay. Okay, the split sample procedure is such that you calibrate from the model parameters from the 0 to here 2. Just 1 second, because I didn't select, here it is. So this is your calibration, and I need to go to the right layer, otherwise it doesn't. Okay, this is your, or let's say here 3. I see that there is a raised hand. Just give me some seconds. This is your calibration period. Calibration. Now, then you have the data in the remaining 2 years which are not used. So what you can do is to use this data to make what? To run the model here, and to perform a validation. Sorry again. To perform a validation. This is your validation. Okay, so what you could do is, for instance, to, let me just put the charger to, I needed to put the charger to the headset. Now, what you could do here is to look at the red part and use least squares to calibrate the model here, and you find your parameter for the model. Okay, and then by using the estimated parameter, you go to the blue part and you run the model and you compute again the sum of squares. What you expect is that the sum of squares in validation is higher than the sum of square in calibration. Why? Because in calibration, you looked for the minimum. The minimum of what? Of the sum of squares with respect to the red period. Now, the minimum for the red period is not the minimum for the blue period, because you found the minimum for a very specific situation, which is the red period. And then when you go to the blue period, it's an emulation of a real-world application of your model, because you are not calibrating in the blue period. You are applying the model. So when you make a design, you apply your model. And this is an emulation of the performances of the least squares, of the sum of squares that you are expecting in your real-world application. So, is it clear what split sample means. And then I give to you the word because I see that you still have a raised hand.
Oh, it's okay.
Okay, very good. And let me lower your hand because otherwise it remains raised. Okay, perfect. Now, what I was saying later is that in doing so, you are reducing the red period for calibration. So the reliability of your estimated parameters is reduced, which is not a good thing. And therefore, what I said is that you may decide to make what? Let me see. Let me show you. You may decide to increase the length of calibration to, for instance, 4 years. Oops, sorry, here I am. You may increase the length of calibration to 4 years. And then, as a consequence, you may reduce the length of your validation to the last year. Very good, okay? Because in this way, you are in a way giving more weight to calibration. But then you may say, yes, but in doing so, my validation is now limited. While you just told me, the professor just told me that it's important. So a way out is to pass, and let me write it here, to pass from split sample to Jackknife. What is Jackknife? It's an iterative procedure. In Jackknife, what you do is, let me just show you by removing these two blue lines, and let me just keep the reference to blue for validation, and 1 second, because, okay. Blue to validate, no, this is not a good thing. Let me just check. Blue to validation and red for calibration, okay. Good. Now I removed it, and now let me do like this. Let's take the first year for validation, okay? And in this case, I have first year for validation and the remaining period for calibration. Okay, and this gives to me what? It gives to me K, let's suppose that I am estimating the parameter K for the linear reservoir, K1, and some squares 1, okay? Let me just move it. This gives to me a first value for the parameter K and a first value for the sum of squares. Very good, perfect. Now, let me now move to the next one. The next one is first year for calibration together with years from, let me just do like this. Second year for validation, and then again calibration. Good. Okay, and this gives to me what? Let me write here. This gives to me, let me reduce the fonts. So not 46 by 30. This gives to me K2 sum of squares 2. Perfect. Okay, now let me move this. I may decide later on to include this figure in my notes. Let's see. And then next one. Next one is first 2 years for calibration, and then years from 3 to 5, and then here in between I have my validation. So you see that you are moving at each iteration the validation period forward. Good. And now here we can write K3, oops, let's change the font again, 30. So K3, sum of squares, 3. Okay. At the end, what you do, at the end, you can take, let me write here. Oops, sorry. Just 1 second. Okay, let me write here. Take the average value of K as final K value. Let me extend it. And then take the average sum of squares as average indicator of model performances. Okay, this is the Jackknife procedure, and I hope it's clear. Ask any question. If not, let me save this because I wanna later on I wanna evaluate the possibility of including it in the lectures. Jackknife. Okay. Very good. So this is the split sample, again, validations. Sorry, it's the Jackknife validation. So we discussed the split sample and the Jackknife. Very good. Okay, and I think there is here the mention to the Jackknife. Let me see, Jackknife. No, there is not indeed. But I think there is not the terminology, but okay, it's here. And the literature also suggested more elaborated validation procedure, like for instance the cross-validation. Cross-validation is a synonym for Jackknife. If you look here, there is, you see that cross-validation, sometimes called rotation estimation or out-of-sample testing, is, and then there is a description. And I don't think here there is the term Jackknife. Let me see if there is. Yeah, and leave one out, cross-validation. It's an example of cross-validation, and the process looks similar to Jackknife. And Jackknife is defined probably in Wikipedia in a different way. By the way, what I see here is that there is a nice picture in Wikipedia which explains what I just wrote in my sketch. You see, here the colors are inverted because, no, are not inverted actually. Test stands for validation, it's blue. This is a curious coincidence. They used the same colors I used, and you see that over the observation period, the calibration is repeated several times. And this is something interesting. I'm curious about the definition of Jackknife. Let me see. Probably they give a different, no, I think it is the same leaving out each observation. Yes, no, it's the same. It's the same as I did. The only thing is that here they refer to leaving out a single observation while I left out a whole here. But it's the same procedure. So Jackknife, you can use it in this case as a synonym of cross validation or rotation validation, whatever. I hope that now the situation is clearer. What I can do is, but you have to give me some time, is to include here the sketch and also the figure from Wikipedia. It's public domain, it's an animated figure, and I think it is a good test. So basically, what is the message, the key message here? The key message is that you have to be aware of what is calibration. So we introduce the linear reservoir. There is a parameter, how to guess the parameter value. And you have to be aware of how to guess it. And you have to be aware of what is validation, which is different from calibration. Validation is a testing in a real world application. You can use different solutions for it, split sample, maybe, or Jackknife, or call it cross validation, which is fine anyway. And you have to be able to explain what is the meaning of validation. The meaning is to test with respect to an out of sample situation, out of calibration sample situation. You have to be able to explain the meaning of it, and you have to be able to explain how you can carry it out, okay? And so this is the message. I think this brings us to the closure of this lecture. And I just would like now to take 10 minutes to make the next step, introduce the Imod model. And I would like to propose to you to work in this way, to optimize our time. I give you a brief introduction to the Imod in these 10 minutes. And then before Thursday, before the next lecture, you have a read at the web page dedicated to the Imod model. You have a read at it. On Thursday, we have 2 hours. My plan is to use 1 hour to illustrate Imod and to use the second hour to introduce the exercise on Imod. I think it would be very useful if, before I discuss Imod, first hour, you have read already the page. If you don't understand something, it's not a problem. I'm not expecting that you understand everything is there. But if you have had a read, I think this would be easier. And I think it would be helpful to reduce the risk that we don't understand each other, because it's a bit complicated. Not really much, but it's a bit complicated. But I think my introduction now, 10 minutes, would be helpful to that end. I'm not really sure if you can split the sample of the next 2 hours in 50-50. Maybe that I need more than 1 hour to explain Imod, and then it means that we will start the exercise on Thursday and we complete it on Monday. In any case, we will need more than 1 hour to illustrate the exercise. Once again, the exercise will be useful because it allows you to get a glance of the real application. And I think, basing on our last experience, that it would be helpful if, even for the exercise, between Thursday and Monday, you have a look at it. You have a look at the R instructions and you have a look at the exercise. But let's concentrate now on the next step. The next step is that I go to the introduction of Imod, and then in 10 minutes. And then after these 10 minutes, I remind you to have a look at just Imod before Thursday, okay? Any question? While I go back and I go to the previous list of lectures, and where are they? Here. And let me open the previous link. Deductive methods. I go straight to the Imod model. The Imod model. Now, first of all, it's again a rainfall-on-off model. It's an analogy with respect to the linear reservoir. It's a similar approach. And it's a similar approach, and let me just say, anticipate, that it's more flexible. It counts 5 parameters. And you see here the first line. The Imod model is a flexible solution, and it's widely used, while the linear reservoir, it's not widely used because it's not really, I mean, the performances are not really good. And the reason is that it's not flexible enough. On the contrary, the Imod model is increasingly adopted. And it was originally proposed just 20 years ago, so it's very relatively new. And so what is the main assumption here? And this is what I want to introduce now in 10 minutes, because I think here, when we talk about Imod, keep in mind that application is easy. You will see in R, it's very easy. It's easier than a linear reservoir. Application is easy. The theory is a bit more complicated. And the reason why it's complicated is that you need to understand the assumptions. So this is why I just wanted to anticipate the assumptions. The main one is the assumption that each point location, look at the screen, each point location I in the catchment, in the basin. So any location identified with I, it's like an elementary area. Okay, let's suppose that you split your catchment into elementary areas. Why do we split the catchment into elementary areas? To deal with heterogeneity, okay? Because keep in mind that the linear reservoir, it's a lumped model. It's a fully lumped, which means that heterogeneity is neglected. Heterogeneity of what? Heterogeneity of rainfall, heterogeneity of infiltration capacity, heterogeneity of lithology, geology. Everything is ignored. Now, when we want to describe heterogeneity, we need to split the catchment into small pieces, into elementary areas. And this is what Imod does for describing a particular form of heterogeneity. Imod doesn't describe all the heterogeneity. For instance, it doesn't describe heterogeneity in rainfall, but does describe some particular form of heterogeneity. What form? Look here. It is based on the assumption that each point location I in the basin is characterized by a local value. So this is a way to deal with heterogeneity. Of what? Of soil water storage, which we call with the variable CI. So what is soil water storage? Let's suppose that you pour water over a sponge, okay? And you put some water into the sponge, and the sponge absorbs water, retains water, stores water. After a while, you get saturation of the sponge, and you start seeing some water leaking out. Perfect. In the soil, it's the same. When it rains on a dry soil, you have infiltration if the soil has some permeability. So you don't see any runoff, okay? If it continues raining, then the soil reaches the max soil water storage, which means that the soil stored some rainfall, but then got to its soil water storage. And then you start seeing some runoff, water flowing over the ground, okay? So the Imod model assumes that each location in the catchment has a different soil water storage, okay? And what is the range of variability of this storage? The minimum is 0, because if you have an impervious location, the storage is 0. Okay. If you have a location that can absorb some water, then you have a storage that is different from 0. And in the catchment, you can identify a max. Typically, it will be in the lowlands. It will be where the soil is more permeable. So you get a storage in the catchment Cmax, where in the most permeable location of the catchment. Okay? I would say that besides the most permeable, I would say also the location with more porosity. It's a combination of issues, okay? Now, this is the main assumption that you have to understand. Each point location I in the catchment is characterized by a local value of soil water storage CI, which varies from 0 to the max value. Why it is important? Because if a location has a storage CI, if you have rainfall less than the storage, then you don't see any runoff. You don't see anything into the river. If you have a location where rainfall is more than the storage, then what you see there, you see the storage, which you don't see in the river, but at the same time, you have an excess with respect to storage, which means that you see some water into the river. And this varies. It's not constant over the basins. It's not homogeneous. Over a basin, usually you have places where, as soon as it starts raining, you see some water into the river, if the basin is impervious. Think about the roof of an house. As soon as it starts raining, then you see some water from the roof falling into the vertical pipes that bring the water into the sewer system, because storage is 0. But in a catchment, there are locations where, if it starts raining, you don't see any water into the river, because the water is retained into the soil. Retained, but up to the soil storage capacity. Okay, you can call it soil water storage. You can call it soil storage capacity. Some references call it soil water retention. And just keep in mind what is the conceptual meaning. Okay. Okay. This CI, which is again, it's the soil water storage, such that if you have rainfall less than it, you don't see any water into the river. This CI is assumed to be randomly varying over the catchment. Okay? It's assumed to be randomly varying. So I need a probability distribution to describe it. So we are not looking into a catchment. Where are the impervious areas? Because we don't want to go at that level of detail. We need too much information. For a catchment, we look at the probability distribution of the soil water storage. We get to the chance of getting that value of soil water storage over the catchment. We look to the chance of getting that value without looking at where it is. Okay? So we don't care about where are the impervious area, but we want to know that in the catchment I have 10% of the area, 10% is frequency and therefore probability. In a catchment, I want to know that I have 10% of the area which is impervious. Okay? And then I want to know that I have another 10%, say, with soil water storage from 0 to 10 millimeters, because we can express water storage with a depth. Okay? It would be storage per unit area. And then I want to know that I have another 5% of chance in the catchment to get a storage from 10 to 15, say. I want to know this probability distribution. Probability distribution of water storage over the catchment. This is the assumption. Now, if you could move forward before Thursday, have a read at this page with these mathematical computations. Okay, and here there is a box dedicated to R. Okay, have a look, and then get up to, let me say, get up to here. So let me find a precise value, not here. So let's have a look until this equation, until here. This is excluded, okay? Let's exclude here. Get to read until this equation included, which, if you want a reference, is just below figure 10. Okay, after figure 10, you have an additional computation, which I would like you to have a look at, because it's an integral, you know, it's better if you look, it is a very simple integral, but it's better if you look at it, because this is the essence of this model. This is the essence of the theory of this model. So have a look at it, because I will, of course, explain it in detail, but if you had already had a look, it would be better. And then get up to the last one, okay? When you get to the above equations allow an easy application, this stop here. Clear? Do you have any questions, students? Okay, let me stop the recording.